Building on our knowledge of double and triple integrals, section 14.6 introduces triple integrals in coordinates other than rectangular coordinates. In particular, we're going to focus on both cylindrical and spherical coordinates that we learned back in chapter 11. So first, I just want to direct your attention to the table at the top of page 1 of the notes, which provides you with all of the conversions and formulas necessary to cross back and forth between rectangular, cylindrical, and spherical coordinates. As always, this table will be provided on quizzes and exams as needed, or if not the entire table, then perhaps specific formulas that are needed. So we get into our first theorem. Theorem 1 here says, let G be a solid region whose upper surface has the equation Z equals G2 R of theta, and whose lower surface has the equation Z equals G1 R of theta in cylindrical coordinates. If the projection of the solid on the XY plane is a simple polar region, which we defined back in 14.3, and if f of r theta z is continuous, then we can write the triple integral over g of f of r theta z dv as the following triple integral. You'll notice what we've done is we've left the outer two integrals as a double integral over r, and then our inner integral is always in terms of z first, where your upper surface is the upper limit of integration, your lower surface is your lower limit of integration, and then everything left out here is a dA, and there's a note where the double integral over r is evaluated in polar coordinates. So in other words, we're going to take this dA and we're going to transform it to r dr d theta. So the nice thing about this is there is no confusion as to which order you're going to integrate with respect to. It's always dz, dr, d theta in that order, and then you fill in the limits of integration accordingly. Now the outer two limits of integration, so these guys right here, those are going to be filled in exactly as you did in 14.3. So if you're still a little bit shaky on that, I encourage you to go back and rewatch the video over 14.3 double integrals in polar coordinates. The only additional thing we're adding in this section is that inner triple integral where you have the upper and lower surfaces that are bounding your region. So how are we going to go about finding these limits of integration? So first, that inner integral is just using the upper surface G2 as the upper limit of integration and the lower surface G1 as the lower limit of integration. And then as I stated here for step 2, you want to sketch your simple polar region in the XY plane in 2 dimensions, and then figure out what your R values are ranging from and what your theta values are ranging from. So let's roll into an example. Use cylindrical coordinates to find the volume. Now, I just want to make a note here that there's not a lot of white space here at the bottom of page 1, but if you scroll down, you'll see that there's even more white space on the next page, so you can budget your space appropriately. All right, number 10, find the volume of the solid that is bounded above by the sphere and below by the cone. So the first thing that I'm going to do is I'm going to just sketch these two surfaces and then identify the region that's being bounded. So first I have a sphere of radius 1. So here's my y-axis. Here's my x-axis and my z-axis. And of course, these are all intersecting the coordinate axes at 1. All right, and so now I want to also sketch the cone. You'll notice that this is just half of a cone. It's not going up and down. It's just for non-negative z values. So this is an infinite cone, right? There's the understanding that it goes on forever, but you'll notice that it actually intersects the sphere and forms this kind of snow cone. It's like a cone with a rounded top. So we want to find the volume of this snow cone. So let me just kind of color it in here. This is a solid too. We're not finding a surface area, but we're finding the volume in here. Now, what I'm going to do first is just set up my volume integral. I know in general, the volume of a solid G is just the triple integral over G dV. Now, we want to kind of flush this out a bit. So first what I'll do is I'll write it as the double integral over my projected region R. And then what I want is my upper limit of integration to be the surface that's bounding above my snow cone. That happens to be the sphere. And so what I'm going to do is I'm going to take this equation of a sphere and I'm going to solve for z. So z squared equals 1 minus x squared minus y squared, or z equals, again, instead of taking a plus or minus, I only care about the upper hemisphere. So I'm going to do the positive square root of 1 minus x squared minus y squared. And so that's going to become my upper limit of integration. And then the cone is what's bounding the lower portion of my region. And that's already solved for in terms of z. And then this is with respect to z. And then, of course, I have my dA tacked on the back. All right, so now what we'd like to do is we'd like to flesh out what this region R is. So remember, you want to project this solid onto the XY plane. So I'm going to do that in green here. And if we just flatten this cone straight down, the shadow we're going to get on the XY plane is just this circle of intersection. So let me highlight it here. The widest part of this snow cone is this line of intersection or curve of intersection. So what I'd like to do is I can see that this simple polar region is a circle. It's clear that cylindrical coordinates is going to be my coordinate system of choice. However, before I can set up those limits of integration, I need to know more information about this projection circle. Specifically, what is the radius of the circle so that I can set up my R limits of integration. In order to determine that, I need to remember what it means for two surfaces to intersect. It means that they share common points that satisfy their equations. So since I already solved for z in both surfaces, I'm going to equate those two z values. So here's my sphere, square root of 1 minus x squared minus y squared. And here is my cone. And then I just like to solve this. So if I square both sides and then I'm going to add that negative x squared and negative y squared over, I get 1 equals 2x squared plus 2y squared. And so finally I get x squared plus y squared equals 1/2. All right, and I conclude here that my projection is a circle centered at the origin with radius 1 over root 2. All right, so rather than drawing a separate picture on the XY plane, I'm just going to use this three-dimensional picture, and I've drawn the projection on there. And what I'm going to do now is I'm going to go ahead and switch everything into polar coordinates at this point. So I'll come back to these outer limits of integration. My inner limits of integration, on bottom, the square root of x squared plus y squared is a single r. And on top, I get the square root of 1 minus r squared. dz stays the same, but then dA becomes an r dr d theta. So I'm going to stick that r in front, and here's my dr d theta. All right, so now let's take a look at our r limits. The radius of the projection circle ranges all the way as small as 0, since it's solid all the way to the origin, out to 1 over the square root of 2. And then for the theta limits, I want the entire circle. So I want to run all the way from 0 to 2 pi. All right, so here is the setup for my triple integral to find the volume. Let's go ahead and integrate with respect to z first. All right, you'll notice that there is no z here. We're just integrating r, which is a constant. So we would tack on a z. I'm going to save one step. I'm just going to note that this goes to rz from those upper and lower limits of integration. So let me go ahead and plug those limits of integration in. So I have r, the square root of 1 minus r squared, minus r times r, which is r squared. All right, so now, of course, this second piece here that I just highlighted, that's just going to be a simple power rule. So we don't need anything fancy there to integrate. But for this first piece, we need a u substitution. So let's carry that out. U equals 1 minus r squared. Du equals a negative 2r dr. And so now let's go ahead and move on to the next piece of white space here. And let's set up our integral. I'm going to begin by just repeating the 0 to 2 pi integral. And then I'll go ahead and leave my limits of integration off since I'm switching to u. And let me take care of this first piece of the integral. I have a negative 1/2 u to the 1/2 power du. And then, of course, I still have my d theta here. And then I'll also just carry out the other piece of that integral. The integral of r squared is going to be a 1/3 r cubed. And this is running from 0 to 1 over root 2 d theta. All right, so now integrating the integral with respect to u. If I add 1 to the exponent, it becomes a 3/2 multiplied by a 2/3. And so what I'm getting here is a negative 1/3 u to the 3/2 power, but I'm just going to go ahead and replace u with 1 minus r squared. And this is being evaluated from 0 to 1 over root 2. All right, and then let's go ahead and evaluate our other term here. I have 1 over 2 root 2, and then of course minus 0 here. All right, so let's evaluate this first piece now. I'll leave my negative 1/3 out front. Okay, so I have a 1 minus, when I square 1 over root 2, it becomes a 1/2 to the 3/2 power minus a 1 to the 3/2 power. And then I have minus 1 over 6 root 2 in back. All still needing to be evaluated or integrated with respect to theta. All right, so let's see if we can simplify inside here a little bit. All right, so I have a 1/2 to the 3/2 power. So that's going to be 1/2 cubed square root, and then minus 1 over 6 root 2. So 1/2 cubed is 1/8. The square root of 1/8 is 1 over 2 root 2. So I have a negative 1 over 6 root 2 plus 1/3 minus 1 over 6 root 2. All right, so those combine to a negative 2 over 6 root 2 or a negative 1 over 3 root 2. And then, of course, plus 1/3. All right, this entire expression inside is a constant, so when I integrate with respect to theta, I'm just going to tack a theta on there. And this theta is running from 0 to 2 pi. So, excuse me, so in the end, I just get an extra factor of 2 pi. And so this ugly constant here is the volume of that snow cone in cubic units. All right, so in this example, problem number 10, was it? Yes, problem number 10, they describe the region in words, giving the equations of the surfaces, and it was our duty to set up the integral entirely. The other way to ask a problem in this section is they can give you a really nasty looking integral in rectangular coordinates and say, look, we can simplify this by using cylindrical or spherical coordinates to our benefit. So make the transformation into the appropriate coordinate system to find an easier triple integral and then evaluate from there. And so that's exactly what this next problem is doing. You'll notice that I pulled this from the chapter review. Problem 21, use cylindrical coordinates to evaluate the integral. All right, so what we're gonna do here is I'm gonna start just by taking a look at the integrand as well as our differentials. And let me just talk about off to the side what those transform to. Remember, x squared is going to become r cosine theta squared, or r squared cosine squared theta. And then dy dx gets transformed to r dr d theta. dz just stays exactly as it is. All right, so we know how to transform both the integrand and the differentials. Now we need to turn our attention to the limits of integration. Now, if you'll recall, these inner limits of integration are just surfaces in terms of z. So those need transformed directly. Now, z equals 16 is z equals 16. I don't need to do anything with that upper limit of integration. However, this one here, x squared plus y squared squared becomes an r squared squared, or r to the fourth. All right, so we've picked off all the low-hanging fruit. It's clear now how we're gonna transform the integrand, the differentials, and the inner limits of integration. Now we turn our attention to these outer two limits of integration. This is hedging back on our information from 14.3 when we were working with polar coordinates. What are these limits of integration telling us geometrically? So what I have here is x is ranging from -2 to 2, and y is ranging from the positive square root of 4 minus x squared to the negative square root of 4 minus x squared. Now, if I squared both sides of this inequality and shifted the x squareds around, this would be synonymous with x squared plus y squared equals 4. So what we're seeing is the upper limit of integration is the upper semicircle, and the lower limits of integration are the lower semicircle of a circle of radius 2. So I'll just briefly sketch what this looks like. Okay. So again, our upper limit of integration is giving the upper semicircle. The lower limits of integration are giving the lower semicircle. And then the question is, do I want the whole circle? So now I look back at my x limits. Had those x limits been from 0 to 2, then I would only want the right half of the semicircle. But since I want to go from -2 to +2, I actually want this entire circle. All right, so at this point, we can now officially transform our entire triple integral. My theta limits, since I want the entire circle, are going to go from 0 to 2 pi. My r limits are going to go from 0 to 2, since I have the solid circle from 0 out to a radius 2. And my inner limits of integration, as discussed before, are r to the fourth up to 16. And then what I'm going to do now is I'm going to include my r squared cosine squared with my r dr d theta. So there's actually 3 r's there. R cubed cosine squared theta dz dr d theta, where this dz is just coming from our original integral. All right, so here's our setup. Now we just need to carry out the integration. Let's integrate with respect to z first. You'll notice that this is just going to pop a z out. So I'm just going to go ahead and skip a step and plug in my limits of integration. So I have 0 to 2 pi, 0 to 2 r cubed cosine squared theta. And when I evaluate my z, I get a 16 minus r to the fourth dr d theta. All right. So next what I'm going to do is I'm going to rearrange, and I'm going to pull my cosine squared out in front since it's independent of r. Now it can't go all the way in front, but it can go in front of my first integral there. So I have cosine squared theta right here. And then I'm going to distribute this r cubed to expand that polynomial. So 16r cubed minus r to the seventh dr d theta. All right. So now let's go ahead and integrate this polynomial with respect to r. Rewriting my first integral and rewriting my cosine squared theta. I have not a 1/4, but rather a 4r to the fourth minus 1/8 r to the eighth. And I want to evaluate r from 0 to 2 d theta. Now plugging in 0 is going to drop everything out, so I'll just plug in 2. And while I'm doing that, I'm going to rewrite this cosine squared using the half angle identity. So let me just write this off to the side. Recall that cosine squared theta can be written as 1/2 of 1 plus cosine of 2 theta. All right, so I'll go ahead and make that swap. And then I will also plug in 2. So 2 to the fourth is 2, 4, 8, 16. And then we have, what, 16 times 4. Let's go ahead and do that off to the side. 24, carry the 2, 64. All right, and then notice on the bottom, we have this 1/8. That is 3 2s. So I'm going to cancel 3 of them. And so it just becomes r to the fifth or 2 to the fifth. So 2, 4, 8, 16, 32. Okay, so what I have here is 64 minus 32 is 32, but then the 1/2 out in front, half of 32 is 16. So I'm going to write this as 16 integral from 0 to 2 pi of 1 plus cosine 2 theta d theta. All right. Now, if you feel comfortable doing the u substitution here in your head and recognizing that that's going to pop out a factor of a 1/2, by all means, you can skip that u substitution. If you still don't feel comfortable making that skip, then go ahead and show u equals 2 theta, du equals 2 d theta, or in other words, d theta is a 1/2 du, and you'll see this factor of 1/2 popping out. So I have 16 times theta plus 1/2 sine of 2 theta, where theta is ranging from 0 to 2 pi. You'll notice here that the sine function dies at 0 and 2 pi, so it's going completely away. And the only thing that remains then is going to be the theta when I plug in a 2 pi. So I get 16 times 2 pi equals 32 pi. All right. So that concludes the examples that I have in cylindrical coordinates. The nice thing about cylindrical coordinates is we've been essentially working with them for a couple semesters now. Polar coordinates really are spherical, cylindrical coordinates, except for they don't have the z component. So that's the only difference. So generally speaking, students find cylindrical coordinates a little bit easier to work with because they're more familiar with it. Now we'd like to turn our attention to spherical coordinates. And so I have a remark here that says a triple integral in spherical coordinates can be evaluated as an iterated integral of the form. All right, so you'll notice here I'm starting with a function that's already in terms of spherical coordinates. And here's the important thing to catch. The differential dv becomes rho squared sine phi d rho d phi d theta. All right, that is a pretty hefty transformation. So when we get to the exam, I'll be providing this formula for you so that you're not memorizing it. You'll notice here a very vague statement of whatever those appropriate limits are. So we're going to do some practice here working with identifying what the limits are in spherical coordinates. But one thing that I want to point out is this order here for the order of integration is fixed. So fixed order. We spent a lot of time in 14.2 discussing how you can switch your order of integration and how it's going to affect your limits of integration. In this entire section, it's always dz dr d theta or d rho d phi d theta. So that's one nice thing about these coordinate systems. There is no ambiguity of your order here. All right, let's take a look at 14. This is another example where they're going to describe your solid and you need to set up your integral from scratch. Use spherical coordinates to find the volume. Find the volume of the solid within the cone, phi equals pi force, and between the spheres, rho equals 1 and rho equals 2. So this actually has a picture that's very similar to what we did in problem 10. So first, let's sketch our spheres. All right, so here's my rho equals 2. This is my larger sphere. Here's my rho equals 1, my smaller sphere. And then we have this cone where pi force is going to be the angle from the positive z-axis. So let me just remind you, phi represents the angle from the positive z-axis. So I didn't even draw it here, but z is coming up this direction, y, and x. And so what we want to do is we want to tilt 45 degrees away from z, and we get our cone. Now, as always, this is an infinite cone, but it intersects the smaller sphere right around here and the larger sphere right around here. All right, so what we get here is we get a solid, and let me maybe kind of highlight it. We get a solid that's like a truncated cone that has kind of this rounded top. All right, so if you wanted to sketch that, it looks like this. And then the rounded top. All right, kind of looks like an ice cream bowl dish. Okay, so we would like to find this volume. And so if we just set it up in generality at first, remember the volume is the triple integral over our solid G dV. Now we want to use spherical coordinates. So what we know is our dV gets transformed to a rho squared sine phi d rho d phi d theta. All right. And so what is rho ranging from? Well, if you'll recall, it says between the spheres, rho equals 1 and rho equals 2. So we don't want anything between 0 and 1. So that tells us our rho is ranging from 1 to 2. All right, what about d phi? Remember, phi is going to be that angle from the positive z-axis. We want the pieces inside that truncated cone all the way ranging from z equals 0 out to z equals pi quarters. Now, you don't want to go from negative pi quarters to pi quarters because remember, it's phi is always going to be positive from 0 to pi. And then when we revolve in the theta direction, that's where we get all of the piece of that chunk of cone. So now for theta, since we want the entire volume of that truncated cone, I want my theta to range from 0 to 2 pi. I want a full 360-degree rotation around there. All right, so here's our setup, and now we just need to carry out the integration. Let's integrate with respect to rho first. So I'm going to copy my first two integrals. And then for rho, I'm going to get a 1/3 rho cubed, where rho is ranging from 1 to 2, of sine phi d theta. So let's go ahead and evaluate at 1 and 2. So I have my 1/3, and then rho cubed is 8 minus 1, so a 7/3 here, sine phi d theta. All right, so next we're ready to integrate with respect to rho. I'll go ahead and just pull the 7/3 out front, rewrite my theta limits, and the integral of sine is a negative cosine. So negative cosine phi, where phi is ranging from 0 to pi fourths. All right, so I have my 7/3. I have my integral from 0 to 2 pi, and I get a negative root 2 over 2 plus 1 d theta. And finally, since I'm integrating with respect to theta and there are no thetas, I'm just going to tack a theta on here at the end, going from 0 to 2 pi. And so I'm just going to plug in 2 pi here. So I'm going to write my final answer as 14 pi over 3 times this expression, 1 minus the square root of 2 over 2. All right, and this is the volume of my solid. We could write cubic units here if we wanted. All right, we have one final example, and it's of the opposite type, where if we're given a really complicated looking integral in terms of rectangular coordinates, recognizing that perhaps it would be easier to solve in spherical coordinates. But first here, we just have a remark talking about the various ways to convert from rectangular to the other two coordinate systems. So this first bullet point here is just saying, look, x is our cosine theta, y is our sine theta, z is z, so you don't need to transform, and then dv becomes r dz dr d theta. And then in spherical coordinates, x is a rho sine phi cosine theta, y is a rho sine phi sine theta, z is a rho cosine phi, and then dv transforms into rho squared sine phi d rho d phi d theta. So again, these things I'm not really interested in you memorizing them. I'll provide them on the equation sheets for the exam, but I want you to be proficient in using these concepts. So our final example for this set of notes here, use spherical coordinates to evaluate the integral. And you can see it looks awful. It looks absolutely terrible. What we see on the inside here right away is an x squared plus y squared plus z squared. We recognize that to be rho squared. All right, so our inside is going to become an e to the negative rho squared to the 3/2 power. And of course, when I have a power raised to a power, you multiply those exponents. So this just becomes an e to the negative rho cubed. So that's going to greatly simplify things. we know that dz, dy, dx is going to become everything up here that's highlighted in yellow. So we're okay with our integrand and our differentials. Now let's zero in on these limits of integration. And in this case, we need to look carefully at our differentials. So these are the z limits. All right, so let's take a look. What we have is z is ranging from 0 up to the square root of 1 minus x squared minus y squared. So we've been working with these types of expressions enough that hopefully you recognize this to be the upper hemisphere of the unit sphere. So let's go ahead and just sketch that. All right, so here's my upper hemisphere that's given by the z limits. Now the question is, are we gonna work over this entire solid, the entire hemisphere? Or are we gonna start slicing and dicing it down to quarters of spheres or eighths of spheres? So that's what we're gonna check next. So next, let's look at our middle limits of integration, which are in terms of y. So what I have is y is ranging from 0 to the square root of 1 minus x squared. All right, so what this tells me is now I only want positive y values. So if I put my negative x here, I'm going to slice this hemisphere in half, and I only want these positive y values. Okay, so I'm going to put a big X over here. We're now saying, look, I don't want to look at any parts of the hemisphere that have negative y values, so I'm cutting that side off and throwing it in the trash. So now the final question is, do we want all of this quarter sphere, or do I want to cut it in half again? How much of these X values do I want? So we'll note here that the X values are ranging from -1 to 1. And so that means I want everything in the positive x-axis and also everything in the negative x-axis. So I do want this entire quarter sphere. Now that we know what our region is, we can begin to set up our limits of integration. So I'm going to leave them blank. And then I'll go ahead and write in what my integrand is, which we previously found. That was e to the negative rho cubed. My e's and rho's look similar. And then dz dy dx becomes a rho squared sine phi d rho d phi d theta. All right. So what is rho ranging from? We're looking at the piece of the solid sphere of radius 1. So that means that rho is ranging from 0 to 1. All right, what's phi ranging from? So we have our positive z-axis right here. How far away from that z-axis do we want to stray? So we want to come all the way down. Here's pi quarters, here's pi thirds. We want to come all the way down to the y-axis. So we want phi to go all the way to 90 degrees or pi halves. So my phi is from 0 to pi halves. All right, and then how about theta? Theta is in the xy plane. So let me pick maybe a different color here. So here's theta equals 0. We want to keep coming around. When we get to the y-axis, this is theta equals pi halves, but we actually want to go all the way around to the negative x-axis where theta equals pi. So my theta limits are going to range from 0 to pi. All right, at this point, we have successfully transformed the triple integral into spherical coordinates. And now what we want to do is carry out the integration. So I want to integrate with respect to rho first. You'll notice that I have two rows occurring here in my integrand. So I'm going to set up a u substitution. I'm going to let u be this inner function negative rho cubed. So that gives me du is a negative 3 rho squared d rho. What I see is a rho squared d rho. So let me solve for that. Rho squared d rho is a negative 1/3 du. Okay, so let's go ahead and substitute. And because it's so easy, what I'm going to do is I'm going to change my limits of integration. When rho is 0, u is 0. And when rho is 1, u is a negative 1. So I'm not writing question marks here. I'm just changing my limits of integration. I end up with an e to the u sine phi times a negative 1/3 du, and then d phi d theta. So now I can integrate with respect to u. So I have a negative 1/3 e to the u, where u is ranging from 0 to negative 1, of sine phi d theta. So that's a negative 1/3 e to the negative 1 minus 1, since e to the 0 is 1. And so now let's integrate with respect to phi. The integral of sine phi is going to become a negative cosine phi. So look, there's already a negative out front here. When I pop out another negative, that's going to become positive. So I have the positive 1/3 of e to the negative 1 minus 1 cosine phi from 0 to pi halves d theta. All right, so let's plug in our limits of integration for phi, carrying along all of my constants. Cosine of pi halves is 0, and cosine of 0 is 1. All right, and now everything in this integrand is a constant, so when I integrate with respect to theta, I just get a theta back out. So rewriting my constants with the theta tacked on from 0 to pi, my final answer here is a negative pi thirds e to the negative 1 minus 1. And so you can see how we took a very complicated integral in rectangular coordinates that looked absolutely awful, and we transformed it. And most notably, our limits of integration greatly simplified. By recognizing that we're working with a sphere, we were able to simplify our limits of integration using spherical coordinates. All right, so this concludes section 14.6. We have one more section in chapter 14 that's going to be over change of variables in multiple integrals utilizing Jacobians. So that'll be up next.